Okay, off we go. Okay, so real quick, before we get back into math, I just want to remind y'all, so the plan, we'll see if it happens. I'm optimistic, but we'll, pending reality, the plan is that we'll start doing attendance checks on Wednesday. So there's a fair amount of organizational nonsense that I need to do before that. I'm doing too much teaching today for today to be possible, so the plan is that I'll do that on tomorrow. I will send y'all an announcement. It'll have a lot of details in it. A lot of what it'll say is don't forget to read the website, right? There's a bunch of stuff already on how all that will proceed on the class website. And there will be an app for y'all to download. Specifically, it's the Canvas app, right? You probably already have it, if I had to guess. And I will include a practice attendance quiz. I think I'm going to title it something like free practice quiz or something like that. And the point is that is your opportunity to make sure that you understand the mechanics. Make sure you understand where to find the quiz, right? How to enter a number into the quiz, how to submit it, how to double check and make sure that your submission actually went through and that you got the appropriate credit, right? You should do all of these things in preparation for Wednesday's start of attendance checks. Okay, so anyway, more about that tomorrow, and so be on the lookout for that email, and we'll get back into the math now, picking up where we were last time. Let's talk about spherical coordinates. It's another coordinate system. Remember we talked last time about polar coordinates. We talked last time about cylindrical coordinates. It's kind of sort of the same thing, but in 3 dimensions. Okay, spherical coordinates is very different. Spherical coordinates, there are different angles involved, at least one new different angle, and a different sort of radial notion of sort of a distance coordinate, if you will. Okay, I like to do these in a particular order. I think this is very helpful. We're going to do them sort of like this. We're going to start off by talking about what is theta. Good news, what I'm defining as theta here is the same theta that we talked about in cylindrical coordinates. So that's familiar. I'm going to point out here that when you talk about that angle theta, it defines what I like to call a half plane. Not that every point you describe with that theta has to be on that half plane, but given a theta, there is a corresponding half plane. And I use this phrase, hinged on the z-axis. The idea is you can almost imagine there's a couple of hinges like that, and as theta changes, this half plane kind of swings around the z-axis like it's a door on hinges where the hinges are on the z-axis. Okay. Alrighty, so that's theta. Let's talk about phi. What is phi? Greek letter phi. Here's the thing about it. How you interpret phi depends on the theta, right? So we need to retain this idea of theta. You've got to retain that half plane. Phi is going to be an angle measured off of, wrong color. Measured off of the positive part of the z-axis. Here's the important part. With the understanding that the positive phi is toward that theta half plane. Right? That's, which direction do you go? Well, always toward the theta half plane. Okay. That's for positive values of phi. Now, of course, if you have negative values of phi, big surprise, you go away from the theta half plane. Okay. All right. Now, between the two of these, given a phi and a theta, that defines a direction. And once you have a direction defined, then we can talk about rho. Rho says, and again, with the air quotes, how far. Again, apologies, that makes it sound like we're talking about a distance. Distances are intrinsically positive. Rho does not have to be positive. Rho is perfectly entitled to be negative, but positive values of rho we would interpret in the direction defined by theta and phi. Negative values of rho, again, just go the other direction. Okay, does that make sense to everybody? Pretty believable? Seems like a reasonable way to describe location. Two angles to define what direction, and then a sort of a distance coordinate to define how far in that direction. Okay, y'all are good at trig. You can use that trig knowledge to look at, let's see here, let me use this color, to look at this triangle. Right? I like to reproduce that triangle over here so I can look straight at it. I mean, it's one of the awkward things about looking at angled planes in space is that, when you look at them kind of sideways and maybe from a little above like we are here, right angles don't necessarily look like right angles, right? It can get a little confusing. So anyway, redrawing, just for sort of convenience, not hard to persuade yourself that R, the cylindrical coordinate R, is rho sine phi. Right? Just a little bit of trig of this triangle. And then Z is this side. And of course, that's going to be rho cosine phi. Again, a little bit of easy trig. And that, of course, Z is one of our coordinates, one of our rectangular coordinates. R tells me, based on stuff I already knew, my other two rectangular coordinates. Basically just, a couple of very quick trig observations here, and we can derive our conversion formulas, our spherical to rectangular conversion formulas. So there you go. Take all the time necessary to, stare, think through the details, make sure you're thoroughly comfortable with all of this. And two things about the formulas. I do suggest that you memorize these formulas. Whoops. Oh, come on. It's already out of charge. So weird. So these formulas, I do suggest that you memorize them. On the test, you'll need them, right? You want to have them snap. For your consideration, though, I will point out, I have never memorized these formulas. Just like the determinant formula or the cross product formula, I never memorized them, right? I had noticed the pattern, right? There's an easier way to think about it. Every time I need these formulas, I think about the trig. I rederive them every time. Because I trust my ability to do trig better than I trust my memory. Everybody's different, right? Maybe you trust your memory better. Okay, cool. Right? But for whatever it's worth, you might have a really good memory for the short term. Maybe you trust that you can memorize these and use them appropriately for the test, right? The night before the test, you sit down and you memorize. But 15 years from now, that'll be long gone, right? And I think it's much better to have the trig comfortable. Does that make sense to everybody? All right. Okay, so let's do a little practice. This example y'all can read. It's very straightforward. But let's do a little practice thinking about the geometry of spherical coordinates. Let's see here. Let me do it. Oh, and there we go. Okay. Thinking about the geometry here. Looking at this point with those rectangular coordinates, which tells you some of the numbers in this picture, and then again, a little bit of trig. Y'all are experts at trig. I know y'all can fill in the blanks as to why this angle's pi over 4, that angle's pi over 3. Make sure to think through those details. So the question is, how do I interpret, with all of that done, how do I interpret these spherical coordinates for this point? Well, first we have to acknowledge we have some flexibility. There's lots of different angles that you can pick, right? Remember, we saw with polar coordinates, you can add 2 pi to any angle. It's just a full turn. You're still pretty much going the same direction, so we have that flexibility of 2 pi's. In some sense, that's boring. We don't really need to talk about that much, right? But what's not obvious is that you can add 1 pi. That just gets you going exactly the opposite direction, and then you can fix that by maybe, like we saw with polar, maybe a negative value of r, right? So the same thing can kind of happen here. But the thing is, we have 2 angles. For each of these 2 angles, you're going to have kind of 2 different options of, do you go the right direction or do you go the wrong direction? And so 2 times 2 being 4, we're going to find 4 different, meaningfully different spherical coordinates for this one point. Now, I'm going to draw some pictures and try to persuade you of how to think about these things. Again, keep in mind time being short and tough choices and all that. So we're not going to be able to, obsess on every detail of what we're about to talk about here. But I think I'm going to give you enough to think about that you can go home and sort of think through the rest of the details, persuade yourself of all the details of all four of these points of view. So here we go. Let's start with the easy one. The easy one, we'll use that angle there. Theta being pi over 3. And then we will go ahead and go the correct direction by choosing phi. Here, keep in mind phi measured toward the theta half plane. Phi here is positive pi over 4. That gets me going the correct direction, and then I will have a positive value of rho to get to that point, right? I think that's the easy one. That's kind of in most cases, the one that you're going to default to because why not? Okay. But here's the weird thing. I mean, you can instead, this would seem like a strange thing to do, but instead of going that way, you could go back the other way, right? Instead of when I do with my arm, instead of a positive value of phi, you could go to a negative value of phi and get to where you're going exactly the wrong direction. And we'll talk about what that value of phi would be, but if you sort of just keep going backwards instead of forwards, in other words, away from the green theta half plane instead of towards, eventually you'd go in the wrong direction, and then you would just have a negative value of rho. Okay, now let's, one more detail on this one that I'll let y'all think about. Now let's talk about what is the value of phi. Given this theta, what would be the value of phi that gets you going exactly the wrong direction? Two ways to think about it. I think a nice, easy way to think about it would be to say, well, that is pi over 4. We've already agreed to that. And then I just want to sort of go a full half turn backwards. And so I would suggest thinking of this as, well, we were at pi over 4, and then we subtract pi. Or if you prefer, you can think of it as adding pi. Suit yourself. Right? And so you could you can call this value of you can call this value of phi down here minus 3 pi over 4. Be reasonable. Or if you want to think of it as going sort of further in the positive direction, you could think of that as 5 pi over 4. Either of those will get you going this exact wrong direction. Is that cool? Everybody on board? Now again, there's a lot of little details to think about, right? Take the time as needed. Make sure to digest all of that. Okay, now here's the thing. There's also, for that same point, there's the other value of theta, where you kind of go all the way around to the sort of, if you will, the exact wrong value of theta. Right? Now again, you have two options. You can say, all right, well, here's where phi equals 0. Why don't I just go directly toward? Again, let's talk about how would we go directly toward. Tempting to want to call that phi equals pi over 4 again. It would, last time, with the other theta, this was what we called pi over 4. But that's no longer how phi works, right? Phi always goes toward the theta half plane. So the positive direction for phi goes this way now. So this angle, back sort of like that, that's now negative pi over 4. Phi equals negative pi over 4. Because positive would go toward the theta half plane. Everybody see what I mean? It's confusing. Right? You've got to give yourself plenty of time to digest all this stuff. So that negative pi over 4 for phi would get you going in the correct direction, and then you have a positive rho. Or, again, You could say, how about I add pi? Now, previously, again, this is a reminder, previously when we did like this, we were subtracting pi because this used to be the negative direction for phi. Now, with theta pointing that way, now this is the positive direction for phi. This is now adding pi. And that would make this direction, let's see here, negative pi over 4 plus pi would make positive 3 pi over 4. It's very geometrically taxing, right? Very confusing. There's a lot to think about there. But I think this is a really nice exercise, a little bit of what I like to call mathematical weightlifting. You could argue that it doesn't accomplish anything. Who cares what the spherical coordinates of this point are? But it'll make you a better mathematician. It'll help you to understand the sort of the geometry and intuition of spherical coordinates. So I encourage you to think through all these details, persuade yourself. By the way, notice how important it is to have a good picture to help you think things through. Don't try to do this in your head, right? Or at least if you're having trouble, right? Doing it in your head makes it a lot harder. So think in terms of giving yourself a nice, comfortable picture. Okay. Everybody all right? Okay. Moving along. Okay, so there's a pretty easy to see connection to longitude and latitude. Longitude and latitude. Oh well, let's set the scene here first. If you take the Earth and place the center of the Earth at the origin, place the North Pole on the positive part of the z-axis, and then let's put the prime meridian over to where it points in the direction of the positive part of the x-axis. It's a pretty standard way to sort of place the globe on an axis system. If you do that, what you'll notice, let's see here, is that east longitude is exactly theta. How convenient. Okay. You'll also notice that north latitude, like that. Well, let's see here. If that's north latitude, is that how phi works? Well, unfortunately not really. Phi kind of goes the other direction from the North Pole, right? So phi is not the same as north latitude, but you can see that they are complementary to each other. Between the two of them, they make up pi over 2. Or said differently, phi is pi over 2 minus north latitude. So a couple of easy relationships there. And then lastly, you'll notice in the picture here that rho, the distance from the origin, aka the center of the Earth, to a point you're interested in, aka a point on the surface of the Earth, well, that is always the radius of the Earth. Does that make sense to everyone? So, nice little convenient relationship. If you know longitude and latitude, super easy to write down the spherical coordinates for that point. Now, what's the purpose of this observation? Well, this is the first step in what I think is a wonderfully clever solution to what might seem like a really hard problem. In particular, let's suppose that you're looking at 2 points on the surface of the Earth, like that. You know, maybe one of those is New York and the other is like Moscow or something. How would you compute that distance? Right? Not the straight line distance, but how would you compute the distance, you know, as the plane flies between those 2 points? Now, there's a clever way to do it, very clever. Let me just point out first, though, that if you think about this question on a map, it's extremely difficult. Right? I'm sure y'all have all seen maps always distort distances, right? And, you know, there are certain maps that have been historically used more and they distort distances dramatically. And then, so people have preferred maps that maybe distort maybe a little bit less, right? But they still distort. They all distort distance. Any two-dimensional map that you print on a flat sheet of paper distorts distances somehow or another. Right? There's really kind of no way around it. So doing business on any sort of a projection, any sort of a map, is how do you even? You'd have to figure out the distortion factor, and awkwardly, the distortion factor is not always the same. It depends on which direction you're going. Oh my gosh, it's extremely difficult. Right? So much better is the following approach, which is to notice that if you know the longitude and latitude, then you know the spherical coordinates, in which case you know the rectangular coordinates, which means we've got an easy way to reinterpret these locations as vectors. And once you have them understood as vectors, you can write down this formula for the dot product, right? Keeping in mind that both of these vectors have a magnitude, which is the radius of the Earth. So this is just the old formula. The dot product is the product of the magnitudes times the cosine of the angle. The dot product is easy to compute. That'll allow you to infer what that central angle alpha is. And that will allow you to compute the distance. Isn't that clever? I think that's really clever. Nice fact. Okay, I would encourage you to, again, play around with this. Make sure you're comfortable with the strategy, at least. You'll notice I did not write down all of the formulas. This is a lot to write down, and it's not like we would combine it into a single formula anyway. It's better to think of this as a strategy, right, than as a formula. I have made some test questions in the past where the question was, I have a hypothetical imaginary planet and two locations on the planet, and I made the numbers where they would work out really nicely, and your job is to compute the distance. And anyway, you can look and find those on my old tests. By the way, I assume you all know that all of my old tests are all online. Okay, cool. All right. Okay, moving along. Oh yeah, real quickie. This is very quick. Y'all can fill in the blanks on this without any trouble at all, I'm sure. But something that comes up significantly, surprisingly, but significantly. If you have a rectangular equation, sometimes you need to figure out how to convert that into a spherical equation. For example, there is an integration technique, very important integration technique that we're going to talk about later, a month from now probably. It's hard to keep track, but anyway, not that long in the big scheme of things. And in order to apply this integration technique, we're going to have to be able to find spherical equations of surfaces. Right, so this is the process for doing that. Basically, the big idea, most of the work here is in just plugging in the conversion formulas. Just everywhere you see an X, put the spherical formula for X. And just plug it right on in. The only other little detail that I'll point out, and we've seen something like this before, but if you have a perfect square, sometimes it's useful to expand that out before you start plugging in the trig, because as was the case here, sometimes when you do that, you get nice little easy rewrites like this. And now you could have plugged in the trig and gone through and gotten the exact same result without making this clever observation. But this identity, x squared plus y squared plus z squared is rho squared, does a lot of that for you. Right? And when there's opportunities to make for less work instead of more work, I vote for less work. Right? So it's a good trick to be on the lookout for. Okay, how we doing? Everybody happy? Okay. Here comes a weird conversation. Frustrating reality. But there are different notational conventions that are preferred by different people, different categories of people, and you have to be prepared for whatever you might see in whatever context. Right? So our book, Colley's textbook, has a certain convention, for example, for spherical coordinates. And that's what we've just talked about, the rho, the phi, and the theta, right? We've talked about all those details. Those will go by different names, different variable choices in, for example, physics classes. Right? So it's very frustrating. But arguably it's sort of unavoidable. So, for example, rho represents a different physical quantity in physics. Right? In physics, rho very often represents charge density. And if you're doing an E&M problem, you need to talk about charge density, and then you also want to do spherical coordinates. You can't have two different rhos running around, right? No good. So the physics convention sort of solves that problem. The big picture here is you just got to be vigilant, heads up, right? So this is on you to always be careful, always be observant, head on a swivel, make sure you know what conventions are being used, and make sure to communicate in the right convention. So I have some rules here. Before I get into the rules, I want to talk about a for example. This is the physics convention. What the common physics convention for how to do spherical coordinates. You'll notice that the radial coordinate here is not rho, it's called r, which would be fine except for the fact that, oh, wait a minute, we, in our system, use r to represent something else, right? In particular, we use r to represent that distance down there. So there is a serious consistency problem here, and we can't get around it. You just got to be aware of it. Right? So heads up on that. Likewise, you're probably going to notice what we have called phi, they call theta, and what we called theta, they call phi. So they switched those. I am not aware of what the rationale was for that. Okay, so anyway, in physics classes, you're going to see a lot of that convention. Okay, now with all of this noted, again, I've already kind of said this, but you cannot just decide that's all silly and I'm going to pick a convention and stick with it. Doesn't work, because people you work with are not going to do that. Right? So I think it's really important to get comfortable with the idea of you doing it in different ways. And I want to point out that really, if you think about it, it's not such a big ask. I'm going to point out that y'all, of course, spend most of your time doing two-dimensional rectangular coordinates, with that being x and that being y. Right? This is what everybody kind of grows up doing, right? But then you take an econ class, and they're not x and y anymore. Now they're like p and q or something, right? Or p and v, I forget. Yeah, p and q. I think it's p and q, right? In different contexts, you might not be plotting some random function. You might be plotting how engine efficiency depends on some sort of geometric angle in the engine design. In which case, maybe this would be called alpha, and this would be called capital E. Now, if y'all were to see this, I assume this would be no problem. Right? Y'all have seen this kind of thing. So you don't have to think of axes and coordinates always being the same letters in every context, right? You adapt to the circumstance, of course, right? So all we're asking is that you be prepared to do the same thing for these other coordinate systems. And so, again, heads up. So again, with the rules, thankfully, Colley, our textbook author, seems to use a single convention. That's the one we've been working with so far, right? Rho phi theta. As a special case of a general rule, when you encounter a question in a context where a convention has already been established, you have to stick with that convention. So when Kali is using rho phi theta, you have to do your work with rho phi theta. And then again, in general, same thing. Whatever the context, exam question, maybe, homework exercise from the AHP, could be, right? If the context establishes a convention, you must stick with that convention. You cannot say, oh, look, hey, I'm a rho phi theta kind of guy, and I'm sorry, I'm just going to have to convert the whole thing over and do this in rho phi theta. Like, you cannot do that, okay? You got to stick with the convention that was established in the exercise or the exam. Whatever the context is, you got to stick with the established convention. If there is no established convention, right? So, for example, maybe the question says, compute the following thing. And then you decide on your own, I would like to use spherical coordinates. Then you get to pick. You get to decide which convention you want to use. Right? It's up to you. All good. The catch is that you must make your choice unambiguously clear. Right? So you gotta make it perfectly clear what your notations mean. You can't just start writing down R's and thetas and phis and assume that we know which convention you're choosing. Right? So now a couple of different ways that you can do this. How do you make your choice unambiguously clear? One thing you could do is you could write down, for example, these equations. If you write that down correctly, right? Well, it's perfectly clear then. There's no ambiguity as to what role is theta playing and what role is phi playing, right? That's implied by the equations. So that'd be perfectly fine. An easier, perhaps, way to do it, I think, would be to use this convention here, where you indicate the three coordinates, such as I did here, right? Spherical. Just make sure that you list your coordinates in the standard order. The first coordinate that you list has to be the radial coordinate, which is rho in Kali's convention, is r in the physics convention. But anyway, make sure that you list that first, right? Then you list what I'll call the vertical angle second. And again, in the Kali convention, that vertical angle is called phi. In the physics convention, it's theta, right? But anyway, so I'm explicitly listing phi here. So, and then lastly, the horizontal angle, sometimes called the trivial angle or the azimuth. I don't know the history on the term azimuth. It's just an old term. It's probably Latin or something. The trivial angle, the reason we call this the trivial angle, a couple different reasons. First of all, no matter how you turn, space looks the same no matter how you turn that angle. In some sense, nothing interesting happens when you rotate in the direction of that horizontal angle. Also, the way the math tends to work out when you're doing quantum mechanics and spherical coordinates, the math on this coordinate tends to be a snap. And it's the math on the vertical angle coordinate that tends to be the nasty part. So the terminology trivial is also a reference to how the algebra works out. Anyway, so with this being established, you always go radial, then vertical, then horizontal. You can just write that down. For example, you can write spherical, rho, comma, phi, comma, theta, and I immediately know that you're talking about the Kali convention, and that's how you set up your coordinates. Does that make sense to everybody? Okay. So again, you've got to make your convention clear if it has not already been imposed upon you by circumstance. Okay. So heads up. By the way, when I was an undergrad, I double majored math and physics, and so in my math classes, I was doing rho phi theta, and then in my physics classes, I was doing r theta phi, and I was just constantly like, okay, so math, and then I would go to a physics class, and then I'd go to a different math class. I'm just constantly bouncing around back and forth between these conventions. You get used to it. It's a little annoying, but you do get used to it. Okay. Okie dokie. Standard basis vectors. We've talked about these before, commonly referred to as IJK. I have a preference. I've talked about this previously. I prefer to call them E1, E2, E3 because, of course, if you have more than 3 dimensions, not rare, right? You run out of letters with that IJK convention. So anyway, whatever that's worth. So these are nice. We use them for a lot of things. They're very convenient. But if you're doing business in a different coordinate system, it can also be really valuable to have something that plays the role of standard basis vectors, but that are nice with respect to other coordinate systems. So, for example, let's see here. Let's pick a point like this. You see here we're in 2 dimensions. We're going to talk about polar coordinates. And at that point, you can talk about the unit vector in the direction in which r is increasing and theta is constant. And from this point, appeal to your geometric intuition, from this point, if you hold theta constant and increase r, you go that way. And a good little exercise, you don't have to do it, it's optional. But a good exercise, if you're in the market for such a thing, is to persuade yourself that this is the formula for E sub r. Right, something to think about. And then likewise, let's consider what if you were to hold r constant and increase theta. Hold r constant, increase theta. If you hold r constant, increase theta, you're going to kind of go around like this. But at that very first instant, you'll be going that way. And so that's what we call E theta. And another good little exercise. Again, you don't have to do it, but I encourage you to think it through. The formula for E theta as a function of x and y is this. Right, so think it through. Right, it's a good little practice problem. I'll give you a hint. Last time we talked about rotation matrices. Right? And notice E theta will always be a pi over 2 counterclockwise rotation of ER. And so just take your ER and do a multiply by the corresponding rotation matrix. Bam, get this. For your consideration. Okay, likewise, blah, blah, blah. Now, in spherical coordinates, the picture gets a little bit weirder. Again, geometric appeal. And you can think through if you were sitting at this point and you start increasing phi. Keep in mind that phi is this angle. Right? So from that point, if you start increasing phi, you'd be going that way. Right? And then likewise for the other points. So good exercise to think through. Try it on your own if you like. If you get stuck, come on into office hours. I'll be happy to walk you through. Right? But persuade yourselves that these are the formulas for those spherical standard basis vectors. How are we doing? Everybody see what I'm proposing here? All right. Okay. Really useful. They're going to come up a lot. We're going to find, we're going to do several calculations where knowing these vectors is going to be important. Okay. Do be advised, though, and you can see it right here in this picture, they're not constants. Right? You look at, let me zoom. There we go. So you look at this picture up here, and from that point, E rho points that way, but if you were down here, E rho would point this way. Right? And if you were over here, E theta wouldn't go into the page, E theta would come out of the page. And they depend on where you are, right? They're very location dependent, not constants. The rectangular standard basis vectors are constants. Yeah.
Wait, sorry, could you explain that again? Like the row and stuff?
Yeah, sure. So let's see here. Let me clean up my mess. Get rid of that. So from that point, if I increase rho, I'd be going that way, right? But if I were instead at a point like here, right? If that's where I was, so it's different theta, different phi, and E rho would be this way. And these two vectors here are not the same. I mean, for one thing, this is pointing fairly upward, right? This is pointing basically horizontal. So yeah, they're just literally different depending on location. It's very, very weird. Yeah. Yes?
Can you explain again why E theta is negative y x0 over r?
Yeah, sure. So that E theta, as it turns out, is the same E theta that you get in cylindrical, and most of the point of that is this formula right here. So where does this come from? Well, we argued that ER is this. Are you comfortable with that one? Yeah. So I claim, for your consideration, no matter where you are in polar coordinates, ER and E theta will always be perpendicular to each other, and in particular, E theta will always be a quarter turn counterclockwise from ER. Does that make sense? And so how do you do a quarter turn counterclockwise? Well, it's a linear transformation. We write it as a matrix. Well, images of the standard basis vectors, that whole song and dance, right? And then just, you multiply the corresponding rotation matrix times this, and you'll get this. Yeah. Yep.
So it's kind of like when you're taking the opposite reciprocal fractions to find the perpendicular slope. It's kind of like that, but in
Oh, I know what you mean. Just kind of like that, but but we're not thinking about slope, we're thinking about direction vectors.
Yeah.
It's sort of the direction vector version of that.
Okay.
Yeah. Right. Okay, so good exercises, good little geometry problems. Again, make sure to realize they're not constants. And so that's going to make the algebra a little bit interesting. We'll see that when we get to it. And keep in mind they don't play nice with linear combinations. I mean, this is such a convenient property of rectangular standard basis vectors, right? Which, just to be clear, these vectors here, right? This is such a nice property of these vectors that it almost seems like, isn't that what it's supposed to be, right? In fact, right, the definition of coordinates, go to a linear algebra class, definition of coordinates is they are the coefficients in the corresponding linear combination, right? So, really nice property of the rectangular standard basis vectors, and nothing like that works. Oh, hang on. Oh, and now this one's died. Okay. What are the forces of battery power are working against me here? Let's see if I'm back in business here. Oh, thank God. Okay. Nothing of the sort works in spherical coordinates. So heads up about that. Okay. One thing that is really cool, and this is a much appreciated fact, they are orthogonal. For spherical coordinates, they're orthogonal, and therefore make an orthonormal basis. It's really nice. Another thing that you can make good use of. Likewise for cylindrical, likewise for polar. Just like with rectangular, they're always orthogonal to each other. Okay, moving along, chapter 2. So the next couple of pages of notes, I'm gonna be really brief. Again, it's a lot, I know, right? But it is stuff that's all just kind of definitions. I think it's all pretty readable. It's just definitions and terminology. So take your time. Do make sure to read that. I do want to make sure to emphasize a few key points. Don't lose sight of the fact that a function is a trio. A function is three things. A function is not just a formula. It's a common misunderstanding. Might not even be a formula at all, right? But very importantly, we also have to keep track of what is what you might call the input space from which you get things you put into the function, commonly called the domain. You have to keep track also of the output space. In what space are we promising our outputs will land in, commonly called the target. And then also, the formula. Now we're going to call it rule of assignment because it might not actually be an algebraic formula. But that's the one that most people think of as being the function is, hey, how do I compute the values, right? But very importantly, it is a trio, all three things. So just for comparison purposes, and this is going to seem like a fussy distinction, but if I look at this function and this function, in both cases defined by student ID number, you give me any element of the domain, you give me any student, the value of the function is, okay, well, what's their ID number? Right? I think they're usually integers, right? What's the difference between F and G? In both cases, we're taking students and we're looking at their ID numbers. I mean, come on, right? These are different because they have different targets. Right? Different targets means these are different functions, even though they have the same formula. Why would we care about such a thing? What's the big deal? Well, it has to do with invertibility. Now, there's a bunch of lingo. Make sure to read the details here. But all of this stuff is building up to the idea of invertibility. So this is a picture of an invertible function. Let me zoom in on this. Domain on the left, target on the right. So for this input, the function takes me to this output, for example. It's invertible in the sense that I can just turn these arrows around like so, and I still have a perfectly fine function. Right? So in particular, this point, applying the inverse function, goes there. Is that cool? So invertible functions are important because we need to be able to invert functions to do stuff like, I'm sure y'all remember in calculus class way back when, arc sine is a useful, like the derivative of arc sine is a formula that allows for a really convenient antiderivative formula, right? And so, okay, well, you can't do that until you've defined what you mean by arc sine, and you can't define arc sine until you have an invertible sine function to talk about. So, for example, down here, right, this is what you have to do to make sine invertible. You've got to restrict the domain so that you're only considering these angles and these outputs, and then everything is perfect, right? For any given green angle, you get a corresponding blue value of the sine function, and furthermore, for every blue output value, there is exactly one corresponding angle, right? So this function is invertible. If I was not careful about how I set up the domain and the target, the resulting function would not be invertible. I don't know what you're talking about. What do you mean arc sine? Which of these several possible inputs am I supposed to assume you meant? Right, when you said invert the sine function, I don't know what you're talking about. So you got to be careful about that. By the way, I have a sort of a preferred way of thinking about this, and that is on the unit circle. I think this is really nice. You can think of those angles and those y's on the context of the unit circle, kind of like this. And notice for any angle, there's exactly one y, and for every y, there's exactly one angle. I think it's arguably a little bit easier to see on the unit circle. Certainly you should make sure to be aware of this. Okay, let's see here. Let me just do a real quick hand wave. Again, there's a lot to be read that y'all can read all the rest of this. Make sure to be aware of these terminologies here and this terminology. And we will pick up here Wednesday. See y'all later. Have a good one.